Hello, this is Mr. Huff, and I want to go through these notes just in case you need a little more explanation. I thought I would do a quick video. So this first one, we're talking about covalent compounds, and that's where two atoms are sharing electrons in pairs, and they occupy the valence shells, so the outer shells, of both atoms at the same time. Some characteristics of covalent compounds. They only contain non-metals. So if you see a metal in there, you are talking about an ionic bond, not a covalent bond. Okay? It is a weaker bond than an ionic bond, and you can prove this. Look at sugar and salt. If you look at those two, they are both white crystalline solids, and if you were to take two frying pans and put them on the oven and sprinkle sugar in one side and salt on the other side and turn them both onto medium heat, the sugar will melt and smoke and turn black and carbonize and be gross, and the salt will just get hot. The salt has a much higher melting point, so it is a much stronger bond. The sugar is covalent and much easier to break down with heat. The molecules have strong, stable bonds, and they mostly exist as a liquid or a gas, in some cases solids, but mostly liquids and gases are what occur when we have covalent bonds. Another feature is they do not conduct electricity. They have low melting and boiling points, like my sugar example. Most are insoluble in water. Most of them, if you mix them in water, they will not dissolve. Okay, most of them. Okay, so these are some general characteristics. Another type of covalent bond that you need to be aware of are diatomics. These are elements that bond with themselves. They will never occur in nature alone. They will always have at least another one of themselves connected covalently. So the ones these are all bromine, iodine, chlorine, hydrogen, oxygen, and fluorine. And you can look on this little periodic table here. Hydrogen, nitrogen, oxygen, and fluorine, fluorine, chlorine, bromine, and iodine. So those are diatomics. So they'll show up with these formulas: Br2, I2, N2, Cl2, H2, O2, F2. Let's look at dot structures a bit. The atoms are going to share the dots, and the dots represent the electrons in the outer shell. You should have that drilled into your brain by now. They're not transferring, so you don't use the charges and you don't do the crisscross arrows. You just keep adding elements until there are enough electrons there to have an octet, 8 in each outer shell. Okay, they fit together like a puzzle, and it's only necessary to show the final products. Always start with the first element unless it's hydrogen. Okay, and that's because hydrogen only has one electron, so it's easier to put it on the outside. And so you can look at these down here. You have nitrogen trichloride, and let me move this out of the way so the little bar disappears. Okay, here we go. Nitrogen is in the middle, represented in red, and chlorine is represented in green. And you can see that there are 3 chlorines sharing with the nitrogen, and so now all of those have a full outer shell. H2, we want 2 electrons in the outer shell, so they share with each other to finish that. If hydrogen and fluorine connect together, 1 hydrogen connects to 1 fluorine, and both have full outer shells. Hybridization, mixing of 2 or more atomic orbitals of similar energies on the same atom to give a hybrid of those orbitals. Let's look at an example. This is talking about group 4A, and on our periodic tables, this is column 14 that starts with carbon. And underneath that is silicon and germanium and tin, okay? And boron, so these 3 elements, boron, silicon, and boron, carbon, silicon, those 3 elements tend to hybridize. And there's a little B6 to remember which ones hybridize. Let's look at an example. When you're writing these down, you show your dot structure like this. You spread the outer electrons around it so they can pair. Same with boron. You have 3 there, so spread them out so you can pair those up. Multiple bonds. Elements can share more than 1 pair of electrons. You can have single bonds, double bonds, and triple bonds. There's no quadruple bond. So let's look at a double bond. Here's some examples. Oxygen and carbon dioxide both have triple or double bonds. And there's a triple bond that occurs when there's 3, and the one that's most commonly seen is nitrogen. So let's look at carbon dioxide. So it requires 2 double bonds to make sure each atom gets 8 electrons, and you can see right here that there are 2 pairs here and 2 pairs here. And if you look at carbon, it has 4 of its own electrons and 4 coming from oxygen on either side, and that gives it 8. And you can look at oxygen, it has 6 plus 2 from the carbon, and that gives it 8 as well. And then nitrogen has a triple bond, so you have if you look at the periodic table, this is in column 15, so it has 6 valence electrons. Let's look at nitrogen. It's a common example of dot structures that have triple bonds. Nitrogen by itself has 5 electrons, so if you just share one across, that gets you to 6 for each one. It's not enough. And if you do a double bond, you get 7. So you have to do a triple bond. So you have 2 out here and 3 on each side being shared. So both of them get 6 plus 2 and 6 plus 2. So that is a triple bond. And again, there are no quadruple bonds. So it's single bond, double bond, or triple bond. Okay? And that's all there is for that.